Hey, my name's Chris Thornton from the UK, and this is my submission for the Lesson 2 assignment for the Introduction to Music Production course on Coursera.org run by Berklee College of Music. This is going to be about analog to digital conversion, or to put it another way, how it is that we turn an analog waveform like this one via an analog to digital conversion process into a bunch of ones and zeros which a computer can interpret and work with. We're more used to a decimal number system. In decimal, we start out with 0 and 1. Those are our first couple of decimal numbers. In binary, it starts out exactly the same. So we'd start out with 0 and 1. Next in decimal, we go 2. Now that's all well and good. We've got enough digits in decimal to be able to do that. However, in binary, we're short of digits. We've run out. There are no more digits. There's only these two. So what we've got to do is stick a 1 in the next column and reset the first column. And actually, we could precede each of these numbers with a leading 0. Now, if we increase the number of digits here, we could go 3, which is 1, 1. But if we want to go to 4, then again, we've run out of digits. So again, we need to add a 1 there, and we reset both of these columns. And then we could go to 5, which would be 1, 0, 1. And actually, we could have a leading 0 in front of both of these, or all of these numbers as well. Now, the number of bits that you include in your word length gives you the amount of detail which you can get in your word length. And it's just powers of 2. So if you've got 1 bit in there, then that's 2 to the power 1, and you can get 2 possible levels in your word. You can get 2 possible outcomes. If you've got 2 bits in there, then that gives you 4 levels. If you've got 3 bits in there, then that gives you 8 levels. So let's say we've got this waveform and we want to convert it to a digital signal. It goes between -2 and +2 volts, and it's being sampled, let's say, at a rate of every 1 millisecond. So 0 milliseconds, 1 millisecond, 2 milliseconds, and so on. -2 here, let's say that counts as 0, let's say that counts as 1, 2, 3, 4, and so on, which we can cover just fine with 3 bits. So our first sample here is 2 at 0 milliseconds, so we'd represent that quite simply as 0, 1, 0, which is the binary way of representing the number 2. Our second sample here at 1 millisecond, well, that's closest to +1 volts, which is equal to 3, so that's 0, 1, 1. Our next sample at 2 milliseconds, that's closest to -1, so that is 0, 0, 1. 3 is closest to 0, 0, 1, 0. And finally 4, 0, 1, 1. So if we were to sample more frequently, we'd be able to get more detail about the wave. Let's say that we were to double the sampling frequency. Then we would get all these extra points, there we go, as well. And that would tell us an awful lot more about what the wave was doing. It would still be missing some of the detail though. We could increase the sampling rate even more, so we could sample here, and here, and here, and here. And the more times that you sample, the more detail you're getting about exactly what the wave is doing, and the more able you are to accurately reproduce it. We're limited to these levels. We can't ever get any more detail than these specific levels, than these particular voltage levels. What we really need to do is be able to come up with a way to be more sensitive to voltage. We need to be able to actually sense this voltage, and this one, and this one, and this one. We get much more detail if we do that, and we get a more natural sound. And that means we need to sample to more bits. If we want to double the sensitivity, then we need to add 1 more bit, because that actually doubles the number of levels which we can look at. The trouble is that if you double the bit depth, then you double the amount of data that you need to store. And if you double the frequency, then you double the amount of data that you need to store as well. This takes us on to the Nyquist-Shannon sampling theorem. What this basically states is that you need to sample at least twice the maximum frequency which you want to reproduce. So the maximum frequency that we want to reproduce as humans is 20,000 Hertz. So we need to sample at least 40,000 Hertz. I hope that's been instructive to you. What we've looked at today is exactly how we turn an analog signal, like we might hear, into a digital signal which a computer can work with. We've considered how the binary number system works, how the number of bits affects our resolution, and when we put it all together, exactly what's going on, and how this turns into a stream of numbers on our computer. My name's Chris Thornton, and I'm really enjoying this course so far. See you around.